perhaps those things are quite different, but the all right. Okay. There we go. So before we get started, next week, I'm not going to be here on Tuesday, so maybe we could meet Thursday instead, if that's all right with you.
Yeah. Thursday, I only like have a TA left.
What time is that?
From 8 a.m. to 10 a.m.
In the morning.
Yeah.
So let's see if we could find a time in the afternoon. I may do it online, but let's find a time. I'll be coming back from California, and so let me see, check the schedule. It should be here, but I don't know the exact time yet. I'm giving a talk in California on Tuesday. I'm supposed to fly back Wednesday. But it's always a bit difficult in the sense that the flights, and because of the time difference, it's 3 hours later. So the flights get in very late to Indianapolis. Anyway. Did you try the homework?
Yeah, I'm working like processing the safety the last one. Like
Okay.
I would like put 2 million this like this year.
Well, so that's fine. I mean, I have some of the homework problems as exercises for class. So we could potentially do some of those together. I mean, if you've already done them, we'll skip them. If you haven't done them and you want to, we could spend, and you're having trouble with them for some reason, then we could work on them together. Right. I did pull all of the exercises, the same exercises, the homework, but they're pretty close. I tried to make them. So because what I would like to be able to do is get to this angiogenesis simulation. There's this classic bacteria macrophage simulation. And then maybe we'll be able to get to, if possible, I'd like to get to this wound healing simulation. That wound healing simulation, in terms of the way the code is written, is probably the one that's closest to doing a physicell model, because that uses explicit forces like physicell, where you explicitly push the cells around in a given direction. And so we'll see about that. I was hoping Pedro would be here because that one, that demo is one that Pedro wrote, and usually he teaches that. I should be okay with it, but we'll see. So this is, according to me, lecture 10, and I want to continue with the chemotaxis. And once we're done with chemotaxis and explicit forces, we've essentially covered the main parts of CompuCell. What we haven't done are links, so rigid finite element links, and we haven't done network models. And Physicell uses MabBoss and libRoadrunner to specify reaction networks, metabolic networks, signaling networks. And so actually the specification of networks in CompuCell and Physicell is the same. So probably that won't be very different. In fact, the Physicell uses code that was originally written by somebody in my group for the libRoadrunner package, although it's now maintained by a group in Seattle. Anyway, we'll get to that next week, perhaps. So today, we're going to talk about chemotaxis and explicit forces. As always, I'm recording this, so you can look at it later if you want to. Oops. Don't know why it doesn't want to do it. Get there eventually. So last time we really ended by doing that chemotaxis of the self-generated gradient. And there's a lot you could do with that problem beyond what we did together. It's quite interesting if you have multiple cells, and if the cells adhere to each other, they behave in one way. If the cells repel each other, they behave in a very different way. You could also have multiple gradients where the cells respond either in different ways to different fields, or you can have a subgroup of cells that responds to one field, one subgroup of cells responding to another field. You could get quite complex behaviors with that simple model. But I thought we could start today with the chemotaxis dependence on parameters. And that's the code I just emailed to you. Hope it will work.
Is email me the code?
Yes.
Yeah.
Or you can download it from the Google Drive. Or you could try to write it yourself, although it's a little bit elaborate to write, and so I wouldn't. And then we didn't do the log scaled chemotaxis in class, so I wanted to make sure that that was clear. And then I wanted to do the angiogenesis simulation. Okay. So last time we did the self-constructed gradient where we started with a chemical field that was constant everywhere, and then the cell consumes the chemical, and then the random fluctuations cause what's called a symmetry breaking, where if the cell moves forward in a particular direction, then it sees a higher gradient in the direction in which it's moved, and so then it tends to keep moving in that given direction. You get what's called a self-avoiding random walk from that. And there are various games you can play. As I say, we did it with a single cell. If you have diffusion so that the trail that the cell leaves behind gradually disappears, you get different results. If you have the medium secrete chemicals so that the trail disappears, you get somewhat different results. And one of the things that I had asked about was if you could possibly, using ChatGPT, write a little code that would calculate, given the position of the cell versus time, calculate what's called the persistence length of the cell. And I don't know if you were able to do that.
Oh yeah, I just tried to write some code. Yeah, like with the systems with ChatGPT and
Right.
yeah, I think that works.
It works.
Yeah.
I probably should add it to the demo because the correlation code to do the persistence length, that's the kind of thing we're doing it by hand. I mean, I've done it by hand in my life, but it's fairly complicated code. And so having a coding assistant to help you with it is useful. I don't know if you want to show us what you got. Pedro's online now. He might be interested. Do you see how it worked for you?
You know, like the code generator.
Well, so did you question, how did you do it? Did you have the simulation run and then save a file and then process the file after the simulation ran to calculate the correlation length? Or did you do it while the simulation was running inside of CompuCell?
I think I just compute it during the simulation. So
Okay, so you put it inside the simulation. I'd be interested just to see the code if you're willing to share it.
just
Hi, Pedro, how are you?
I'm good.
While she's doing that, it looks like I'm going to be starting Portuguese lessons at the beginning of April.
Nice.
I'm going to have to modify my schedule because I'm going to have to do that 2 hours a day, 5 days a week.
5 days a week. Oh my God.
Yes, the legal requirement is 150 hours of class time.
Well, that's also the fastest way to learn a language is to put a lot of time on it. So
Yeah.
it work.
Okay. So here, so go ahead.
I'm not pretty sure when it works.
So you're not sharing. Okay, there we are. Okay.
I'm not sure if it like works correctly.
That's okay.
I'm pretty sure like it could run. So so this is how I compute the velocity and stuff. Like just trying to compare it.
Right. So
After
the
time interval, like how much the center of the mass moves. Like
Right.
X direction or Y direction, and then just
Mhm.
compute them. And
So you calculate the instantaneous velocity in lines 30 and 31.
yeah, so like by far it's computing like all of
Okay.
these are computing the velocities. And so because we're not sure about the lag, because like if you're computing the correlation, the self correlation
Right.
itself, you need to like define a time frame.
Right.
But like because you don't know the exact time frame or like how much it should be, so it's just like set the maximum
Right.
limits for the
Right. So you explore up the right. So let's see before let's just before that. So actually, line 33. I don't know the set default.
Oh, it works.
What is that function? Do you know what does that function do? Pedro, do you know that function? The append makes sense to me, but I don't know what the set default does.
I think it is
Just set this is the key and this is the values.
I think it's telling the dictionary to receive lists, but it does that by default already. So I think this is just doing nothing.
Yeah, I would have just written cell.dict parenthesis quote v history dot append.
Exactly.
But in any case, I mean, it's not, I don't, if it works, it works. It's just, I've never seen that function. Python has so many different functions in it, it's hard to, okay, so.
I think I know what it is, James. So you have, when you do append, it has to be a list already, so you have to instantiate it somewhere. So here, I think because she does not instantiate somewhere else, it has to tell the dictionary to append to something that is an empty list.
Okay, so instead of in the start function doing cell.dict quote history equals blank equals blank list, this is basically creating that blank. It either says either append it or create a blank list. Is that right? If it doesn't exist already.
Yeah, that's what I think.
Okay, that makes sense. Okay, it's good to know. I learned something. You taught me some Python. Thank you. Okay, so now we have a list with all of the instantaneous velocities. And now you say every 100 Monte Carlo steps,
calculate.
right? We see how long, if we have enough points, because if there aren't enough points, it won't work.
Yeah, so like, if we have like over 50
Right,
points and then, but
Oh.
no, like, no more than like 200 points.
right. So now you're going to do correlation. So you do a mean squared velocity, instantaneous velocity. Okay.
It's like if we have 50, let's say if we have like 50 data points or velocity points here, and given the lag to be maybe 4, so just compare
Right.
without velocity 4
Right.
and velocity 5 and velocity 2, velocity
Right.
6, and just compare them. So
I guess I would have thought in line 48, we'd use something like max lag is n over 2 instead of n minus 1, but that's okay.
probably just this like threshold.
Well, it's more if the lag is very big, then you don't have, then you only have 1 or 2 points in the overlap range. But it's okay. Okay. So now you do 4 lag in range. Now you do the dot product to get the correlation normalized by the mean. Right. So R is the autocorrelation for that lag. Yeah.
Yeah.
Okay.
So just those all the R's or those pairs into a list. And then like we just compare whether the correlation is smaller than 1 divided by 10.
So if you plot the correlation versus the lag, well, I might, at least to begin with, put in a plot, which you'd have to clear every time, but which plots the correlation versus the lag to see what the shape of that looks like. Because on the one hand, it might be a simple exponential decay, in which case your fit here would work. But sometimes the correlation doesn't behave the way you expect. It might have a peak somewhere or not have the shape you expect.
Yeah, although if this threshold is not very reasonable.
Yeah, if you have too few points, it could behave strangely, or sometimes there are all sorts of situations in which the correlation function isn't a simple decaying exponential. Which is not to say that what you're doing is necessarily not right, but it means that it may not.
I mean, like, that makes sense because we should test if the calculation is reasonable. Yeah, so like I just ran this simulation with different parameter tests and calculating the LP. Maybe I'll just record them into like a separate file and then like use those collected data to plot. So that's my plan.
Oh, that's fine too. Pedro, how did you do it when you did it? To get the correlation length?
To get the correlation length, I fit the MSD curve, but you can do the autocorrelation, the velocity autocorrelation as well. You have to fit, in the case of the autocorrelation, you can simply fit a decaying exponential and say this is approximately the, or a proxy to the persistence.
The correlation time, yeah. I mean, that's what she's doing here.
Mm-hmm.
It's not a formal fit. You're just looking for You're just saying, when does the value, at what time what lag does the value go to 1 over E to the value for 0?
Yeah,
Which
that could work.
which is okay if the correlation curve is well behaved.
Yes.
And
In
of
the
course,
case of
if the correlation curve isn't well behaved, maybe there is no single correlation length, right? It could be that the correlation length assumes that the trajectory is statistically homogeneous in a particular way, that the trajectory's behavior doesn't change in time.
yeah.
And it's possible here that the trajectory behavior does change in time because the pattern gets crowded, right? Initially, the cell can move anywhere, but as time goes on, parts of the space are excluded. And so the correlation length might actually change in time a little bit. So it's not, I wouldn't be too worried about the details of the correlation length because of that. But it would be interesting. If you look by eye, you would say that the correlation length here is about 20 to 30 lattice constants, I would say. Maybe a little more, maybe a little less, but certainly more than 10 and less than 40. And so if the number that you're getting is in that range, then probably the estimator is pretty good. So when you ran it, what did it give you for the estimated correlation for the persistence length?
Persistence length is pretty small. Actually, like okay, let me just reshare my screen, include the terminal and stuff. Let's share the
Because we'd also have to convert, right? You have something which converts the time back to a position, right? Because you have the mean speed, and then you also have the correlation time, and so then the mean speed times the correlation time gives you a length. So yeah, what you've got there.
Yeah, it's
Right.
not like part of the 40 or 50.
Persistence length is 0.12. Yeah, that seems
Maybe I'll just link to
that seems not right. So maybe it hasn't run long. Well, you've already run 1,000, 2,000 time steps.
yeah, like over.
Yeah. So I would add something to plot the correlation function, because it's possible that something's happening to that correlation function. For example, suppose that there were very strong in CompuCell, something that can happen is that it's not unusual for a cell to add a voxel and then immediately remove the voxel. So the center of mass moves forward and then backward at the next time step. And that could lead to an anti-correlation of the velocity over very short times. And in that case, there might be the correlation is high, goes very low, and then comes back up and then goes down. So that's why I think it's important to plot, at least for a couple of times, what that correlation versus the value versus lag is, so that you could see what the shape is. Because again, your assumption is the shape is a smooth decaying exponential. And if it is, you're fine. But if it's not, then you have to think more. And sometimes what you get is something that's spiky where the envelope is a smooth decaying exponential. So why don't you try, could you just add a plot of of that correlation? You've got everything you need there. And I would use dots rather than lines when you plot.
This one.
Yeah, where it says style.
Oh,
Yeah,
oh,
the extra lines usually are a little confusing to the eye. Okay. Yeah, so after line 79,
But yeah, but a lot is, so if you want.
well, okay, so you could put so if you wanted, you could just add a point, which is lag, comma, R after line 76.
Mm.
Yeah, just there, where that right there.
The eyes.
So you need to add, you need to add, right, add a point, a data point. Was it underscore or dash?
Yeah.
Okay, underscore is fine. Just R. Yeah. And you may want to add a race plot, but for the moment, let's just look at that. That's good. Let's see how it works. Yeah, so the correlation is near 0. That doesn't seem to me to be right.
It is like the sound.
The average is not though, James. That this is one of the problems. She's plotting a scatter plot, and it's very difficult to visualize the trend. But maybe there is a trend there, and because
So
it's a single cell, it's not self-averaging, so it's hard.
So let's erase, before we plot, but before, let's go back to your code, the code for a second. And before the loop, where you calculate the correlation, so line 56, maybe, line 56, you want to put, you want to erase the plot. There we go. And I don't know why it's not auto scaling on the y-axis.
But if you're trying to, it's just like draw every lag between 0 and 200.
Right. So that's okay, but but you notice there's no decay. It doesn't look like the values don't seem to be decreasing, right? They're all basically noise. So that autocorrelation is not, the autocorrelation is not doing what you would expect it to do. So let's look at the autocorrelation function and see if there's something funny about it. So you set the correlation to 0. Dot sum is 0, count is 0. Ryan wrench and minus lag. And minus lag. Okay. So you look at the value now and the value of lag forward. Okay. And then you do a dot product. of the two. And then you do a sum, which is in fact the autocorrelation, and you divide by count and the mean. That looks right to me, Pedro. Do you see anything wrong with that? I mean, to me, that looks like it should give you the right answer. I don't know why your correlation is effectively 0. Oh, well, you've normalized the correlation by the number of points in V mean. So expect the maximum correlation to be 1. So let's go back to, let's see the plot again. Let's look at the plot again. Yeah.
It's like, to have a little bit, and it was just turn, the range to the 4.
Right, so it is a positive number between 0 and 1, which is okay.
Yeah, and you can see like maybe since here it's.
It is
smaller
going
than-
down a little bit, you know, it
Mhm.
is.
But like initially it's just smaller than 1 over E, right?
Right, so then it's always giving you one step because it's not looking at the longer time. But it also doesn't look exponential. Can we rescale the y-axis? Is there a point at 0, 1 or not? I don't see a point at 1. Whereas for a lag of 0, the value should be 1, right? And I don't see that point. But then can you right click over that image? Okay, do y-axis, go to y-axis. And then click auto scale. Okay, there we go. Okay. Looks like it looks like auto scale doesn't give the y coordinates correctly anymore, but in any case, it did do it. So yes, it is decreasing. But you could see with that noise, a simple threshold isn't going to give you anything. You'd have to do a fit. You'd have to fit that. We'd have to fit that data series with a smooth curve.
Oh, I see.
So what you could do, for example, would be you could use something like the NumPy. Oh, what is it? There is a SciPy function that'll fit to an exponential. It will give you the decay length of an exponential. I know that.
So you use the like data after fitting the curve and then try to
Right.
calculate the threshold
Right.
of the lag.
Well, I don't think you could use a threshold because look at your data set. If you have a threshold, what threshold would you use? What you have to do is fit. You have to do a fit. You're trying to fit to an exponential. You'd have to fit the data set to an exponential and then get the exponent from the fit, not from just from a simple threshold. What do you think, Pedro?
I agree. And I also think she should be smoothing this out because we don't know what part of this data to select for the fit as well.
Yeah, it's pretty noisy, but I'm not sure how you do the fit.
I mean, you can do the fit like this. It's not a problem. The issue is there is negative autocorrelation at a small
Time, small lags, yeah.
You would like to skip that.
Yeah, so maybe start at time 10 at a lag of 10 or something like that.
Yeah.
Yeah. And then do a fit to an exponential fit. And I know there's a SciPy function that does that, but I don't remember how you invoke it. But the first 5 for 10 points. So. And then I think then if you do that, you'll get something that looks more reasonable. It's still going to jump around a bit because you only have one time series. And so it's going to be noisy. So every time you do the fit, you're going to get a different value. So then you're going to have to do some averaging of the value of the persistence time over time. But as a matter of principle, when you're doing simulations, I think it's a good practice to display the intermediate data. The way we have here, where we've plotted the correlation as a function of the lag to see whether it has the structure we expect. Because as you point out, it is decreasing. As the lag increases, the value decreases. But the noise is so big that you can't do anything simple with a threshold.
Oh, so I have a question. So,
Yeah.
if I use the exponential to further fit this data, like the fitting curve is still like the maximum value is still like the over 1. So I've just learned the definition of the algorithm of like self correlation.
Yeah.
This morning it says like we need to find the exact lag that makes the correlation value smaller than 1. I'm not sure like if it's correct.
Well, so what you really want to do, and boy, I wish we had a whiteboard in here, is, I mean, suppose that you had a cell that just moved continuously in the same direction at the same speed all the time. Then the velocity would always be the same. And the autocorrelation would be 1 for every lag.
Yeah.
For every lag. Suppose that it almost goes straight, but it gradually turns. Then for short times, the autocorrelation will be close to 1. And once you get to the time it takes to turn, the autocorrelation will go down. For example, if you were moving around in a circle, would be an example of that. Now, for a classic noisy system, the autocorrelation for example, for a system that's moving in a circle, you actually are going to have something funny where the autocorrelation, depending on whether you go all the way around the circle or not, the autocorrelation will come back up as you get back. If you do what you're doing here, what you would expect classically is that you would get a decaying exponential curve. Now, what you want to know is the exponent. The curve goes some constant times e to the t to the minus t over alpha. What you want to know is what that value of alpha is. If the curve is perfectly smooth and noise-free, then measuring the amplitude of the value at 0 and finding where it crosses 1 over e gives you the value of alpha. But in a noisy system, you can't do a threshold. You have to fit the curve, and the fit will give you alpha as a parameter of the fit.
Yeah, I know like if you find a curve, that would like not be far enough. I mean, like the curve would be possibly buried in those noisy data, right?
Well, you won't see it, but the curve will still have an exponent associated with it, which is the number you want. So the curve will be larger at 0 and will decrease to the right.
Yeah, we see like the maximum here, the envelope line could be
Right.
under 0.2.
Right.
0.2. So that's already about smaller than 1.
Right, but you're not going to care about what the absolute value is. You're only going to care about what the exponent is.
Oh, okay. Oh, okay. I think I catch.
So again, I wish we had a whiteboard in here.
Probably like is the like coefficient times by the exponential function.
Right. So you're concerned that the value is never close to 1 anywhere in here.
Yeah.
Right.
But we could just adjust.
And so the reason for that is that the system is noisy. And so if there is short time fluctuation, that means that even over short times, suppose that, let's give you an example. Suppose here's an example. Suppose that my actual velocity goes from me to you with no change ever. But suppose that I do that by going jump to the left, jump to the right, jump to the left, jump to the right, jump to the left, jump to the right, jump to the left, jump to the right.
So like counting that by average, like the correlation would never be close.
Right. The short time correlation is very small. It's small because I keep going back and forth. However, the value never changes because on the long time, I'm always going in the same direction. And so you can't assume that the behavior for very short times is the thing you're looking for. There could be multiple time scales in a process, and those different time scales can have different statistical properties. And in this case, there's a short time anti-correlation, which knocks down the overall correlation. But then there's a long time decay of correlation, which you see. Pedro, go ahead. You don't have to raise your hand. Just go ahead.
Yeah, so I am learning Bayesian inference now, and I think Bayesian inference could solve this problem sequentially in the sense that you update your belief about the parameter persistence as you acquire more data, and you do this as the simulation runs because it's iterative. It's an iterative method. You don't need to wait to get a full data set and then calculate and then fit. It's sequential. You do this at every step. But I'm still learning how to do it. Just a curiosity. I think that can solve the problem.
Right. The other thing is that here we've assumed that there's only one correlation length or one persistence length. In fact, there could be multiple time or length scales in this problem. And so we're imposing our hypothesis that there's a single correlation length or persistence length in the problem. And so trying to do a Bayesian estimator where you allow it to have multiple correlation lengths or persistence lengths is also possible. Then you have to have some criterion for how many you're going to have and so on. I think for today, if you're willing to, why don't you, when you have time, look up how to do an exponential fit to a data series. And it's not, again, you could ask ChatGPT. There is a SciPy function which will do it for you. You give it the data and it will return A times e to the minus t over alpha plus b for the displacement. And what you want to know is what that value of alpha is and the uncertainty in it. And then you could use that, and you could overlay that fit onto the, I'd recommend whenever I do a fit, I always plot the fit on top of the data set to make sure that it fit right. Pedro and I, the other day, were doing some fitting. And again, we're lazy, so we'd use ChatGPT to do the fit. And he had 6 data sets, 4 of them fit perfectly, and 2 of them the fit was totally rubbish. But if you only got the parameters out of the fit, you wouldn't know that the fit was bad. So it's always a good idea to check by plotting it on top. So so in a sense, these issues that we're bringing up here, I think are useful to go over because they're not specific to CompuCell or any particular approach to modeling. These are general problems when you have complex models. How do you understand the time series coming from them?
Yep.
And so you might very well run into the same problems in other situations, maybe not exactly this problem, but the same kinds of questions. And so I think it's important to think about how do you display information that allows you to judge whether the fit or the numbers that you're coming up with make sense. And if they don't make sense, what can you do to gradually refine your modeling and provide you more information to understand what's going on? In this particular case, because I've done this a lot, I have a pretty good instinct of why it might fail. But so I mean, if you want to try doing it here in class, we could do that, but
I think it's pretty clear about the
right. Right. And if once you've tried it, email me. And if it's not working or you want to show, if it does work and you want to show me, or it doesn't work and you're confused, email me and we'll meet and we could go over it. Okay. Great. Okay. So let me borrow the screen share back and we'll keep going. Thank you, Pedro. I think your point about a Bayesian estimator is also interesting. I mean, here she's actually making the lag time longer as there's more data. So you are assimilating new data as the series gets longer, although you also cut the lag off at 200. And that may or may not be long enough. You'd have to look at how in units of length, a lag of 200 time units is how far does the cell get in the time 200? Because you may actually have to run the lag out to 1,000 or some longer time. And again, you really have to look at the image to do that. The other thing that you have to worry about, which is a pain, which I wish CompuCell did automatically, is that you're running in periodic boundary conditions. And so if the cell crosses the boundary, the instantaneous speed gets messed up.
Yeah.
So then you have to look to see, did the X position cross the boundary to the left or to the right, or to the top or the Y position to the top and the bottom? And if it did, then you have to wrap the position of the coordinates. And I know Gilberto has code to do that, and I think you wrote code to do that too. But handling the, in other words, so if your position is currently X1, X now, Y now, and your position that is X next, Y next, you have to check if X has gone from near 100 to being near 0. And in that case, you have to subtract 100 from X now to get the right answer. And similarly on the other sides. And so you have to check if you crossed a boundary, you have to wrap around the boundary to get the instantaneous velocity. And it's not hard to do, but you have to check, did I cross the positive boundary? Did I cross the negative boundary in X and Y? And correct for that. So that's a couple of lines of code to do that. If you don't do that, for trajectories that do not cross the boundary, you're fine. But when you do cross the boundary, you'll get a spike where the instantaneous velocity is very, very high. And that will kill the correlation. So your correlation will suddenly go zero. And that tends to make a mess of the calculation. So that's another thing. I don't think in your simulation you were having that as a problem, but it can be a problem.
So yeah, theoretically there could be this algorithm.
Right. And so you need an algorithm that says if the X position is between 90 and 100, and then the next position is between 0 and 10, then instead of making the initial position 90 to 100, you make it whatever it was minus 100 and calculate the velocity that way. And similarly, if it went the other direction, you have to add 100 to it. And so there are 4 conditions that have to be checked. And I wish there were an automatic way to do that. But whenever you do periodic boundary conditions where you're tracking coordinates, you have that problem. And so again, that's the kind of thing where ChatGPT will know the answer. In other words, you tell it, I'm tracking a particle in periodic boundary conditions. I need code that checks if I crossed the X and the Y direction and corrects for that, and it'll do it. It's not hard. It's not hard to do, but you do need to do that check. Otherwise it'll every time you, and if you look at the picture here, you can see that the particle crossed the boundary a lot.
Yeah.
So it's not that it's something rare that you could avoid thinking about. So actually there's a lot to learn from this one little exercise. And again, almost all of it is not unique to CompuCell. These are general problems of spatial simulation and analyzing movement of particles. So one thing we have to remember is if we're going to use chemotaxis in Python, we can add on the fly, we can add chemotaxis to a cell by saying cell, comma, field name with the add chemotaxis data command. And then we could set, for example, lambda chemotaxis. And we could also read the lambda for the cell and change the value. Now, so the next exercise that I was going to do was this one where we do chemotaxis dependence on parameters. And this one, I think, doing this by hand is a little bit tedious. So I would try downloading the code that I gave you, if you can. I emailed you a code. It was called chemotaxis dependence on parameters. And let's see if we can run that, if that'll run. Now, CompuCell does offer a variety of parameter scans, which are wrappers, where it runs a script where it runs the simulation many times for different parameters. And that's really, quote, the right way to do parameter scans. I actually like to do parameter scans inside of a single simulation so that I can display the results while the simulation is running. And so does that run for you?
Yeah.
Okay, so do you want a screen share? Let me give you back the screen share there.
This is the code.
Yeah, so let's look at the let's run it first and see what it does. So your share is not, oh, there it goes. Okay.
Yeah,
All right.
I'm trying to find out.
Okay, there it is. Okay. Yeah, that's one problem. On a PC, you can do that. You can auto layout, but on a Mac, you have to find the windows yourself. There you go. That's all you need. So now run it. So hit run.
Yeah, it's from
Okay, good.
Chemotaxis.
That's fine. So what this does, there we go. So what this does is it runs, it looks at where the cell is. And if the cell gets close to either the left or the right end margin, it changes the direction of the chemotaxis. Otherwise, if the cell is moving very slowly, it waits a certain amount of time and then calculates the velocity. So this is not an instantaneous velocity, it's a velocity over some time. And so the x, and then it changes also the value of lambda as well as the sign of it. And so here what you see, and here I've done it with exponential spacing. So each time you run each time it reverses, it increases the value of lambda by a fixed ratio. You might want to do it instead, adding a fixed number to lambda instead. But if you don't know the initial value, then the ratio makes more sense. And you'll notice here that the maximum speed is saturated.
Yeah.
And so if you just hit pause, don't hit stop, but hit pause. So if I look at the time curve here for lambda, you'll notice that between 0 and about, oh, I'd say 300 or 400, it's pretty much linear.
Yeah.
And then above 1,000, it basically, the speed is independent of lambda. And so what that's telling you is that for this cell and all of the other consistency with this field and this cell, a meaningful value of lambda chemo is between 0 and maybe 300. If you make lambda bigger than that, it's not doing anything. It's basically saturated. Now, knowing that, we could go in and do the simulation again with smaller steps and look closer to what happens near 0 and look at the saturation. So I'd fix the range of lambda then between 0 and 500s, for example, and make the steps smaller and see what's happening. And you'll find that if lambda is too small, it also doesn't work very well.
You want to change the code here?
Well, so let's look at the code together. There are a bunch of parameters. So for example, maximum switch time is if the cell's moving very slowly, I don't want to wait for it to go all the way from one side of the simulation to the other because it's boring. So the maximum switch time is 100. And that means that if the cell isn't moving it is not moving enough, I just give up. I stop. I don't wait for the cell to move too far. then I have the lattice size here. I impose that. And actually, I think I'd have to check. I don't remember whether that's just the value from the simulation or whether I could actually change it myself. And then there's something else, which is these are noisy simulations. And so if I just do one instance of going left to right, my estimate of the speed is going to be pretty bad. So this line 16 where it says self.n flips equals 3, that's the number of repetitions I average over. And so if I made that 10 instead of 3, the simulation would be 3 times slower, but also I'd get better averaging so that my results would be more accurate.
So like the plot prism is kind of like a result after 3 times calculation.
Right. So if you go back to the simulation, there should be a window that plots the position of the cell versus time. Where is that window?
Oh, here. Isn't it? No, it's not.
No, it's the position. There's another window that should say position versus time. Maybe it's turned off in the simulation. I don't think so.
Oh, here. There's another window.
No, I'm not sure what that one is. It actually tracks the position of the cell. It'll be a zigzag. So if I come back here to my screen, it should look like this plot.
Wow. So that means like because the like velocity is increasing. So like the
So
distance.
so what happens is I start the cell moving in some direction. Either when the cell gets to the edge or after some time, I reverse the direction of the cell. After that n flip number, I then say that's the value of speed I'm going to take from that for that parameter. Then I change the parameter value and run the thing again. In this case, I think I've actually set n flip to 2. And so I do it, I may even be 1. So I may have set n flip to 1 here. So it changes the parameter value after every oscillation. But if I did 3, it would be 3 of the same thing and then increase, and 3 of the same thing and then increase. And so what I'm not sure about is I don't know why you don't have this plot of position versus time. Maybe the version of the code that I shared is not, there you go. I just saw it.
Yeah, but it's like moving to the corner. Yes.
Yeah, well, sometimes when you have screen share, it's, there you go. There you go. So that's it. So you see, it goes back and forth 1, 2, 3 times, and then it goes back and forth 3 or 4, maybe it looks like 5 times actually. And then it changes the value and then increases it again. So that's the trajectory of the cell that's being used to calculate the average speed.
Yes.
Right. And then if we look, let's see where this is all in the start function. Those are just initial, those are basically putting things out of range so that they're not 0 to begin with. So let's look at the step function now. So we're doing basically the same thing. Hold on a sec. So you're doing this. First, we're plotting the position. That's line 68 and 69. And then line 70 and 71 are basically doing what you did in your simulation, which is appending the position. I'm not calculating the velocity first. I'm just putting the center of the position. So line 70 and 71 are accumulating the X position and the Y position. And then in line 76, I'm basically asking the question, if the cell has moved, sorry, if the cell has, what happened? Oh, I'm looking, sorry, excuse me, go back to you'll have to reshare. I forgot that I wasn't sharing that. I have the same code open on my desktop, and so I was thinking, oh, I'm sharing it, and so of course you're sharing it. So so if I look in line 80, this says if the cell gets to be close to the edges of the simulation, or the time clock has run out, then I reverse the direction. That's what line 80 does. And then I also count if I reverse direction n flip times, and if so, then I increase here in line 99. If the number of flips is bigger than n flips, then I update the value of my parameter. I evaluate the mean speed, and then I also update the parameter. Where do I update the parameter? The parameter update is where? There it is. It's in line 107. Now, in this case, and then I actually apply that update in line 113. Now, if I were going to change some other parameter instead of the lambda chemo, then lines 112 and 113 would be different, because it would be changing lambda volume or V target or something else. But I could use this basic framework to do parameter scans for any parameter. And I could also, instead of in line 107, I say current value times equals self dot step ratio. So that's a multiplicative, that's an exponential parameter scan. If I did plus equal step ratio, then that would be a linear parameter scan. So I could use the basic code architecture here to evaluate the effect of change of almost any parameter on, in this case, cell movement. So again, the point here is not the detailed code necessarily, but to think about how would you do a sensitivity analysis. How would you tell how the behavior you care about depends on a parameter? And again, in a classical simulation, you would do that by running lots of simulations with different parameter values. But the problem with doing that way is that then you have to post-process it. And until you post-process it, you don't know what you got.
Oh, what does that mean?
Well, suppose that I ran each one of these flips as a separate simulation.
Mhm.
I'd have to run 50 simulations. And then I'd have to write some code to post-process it to see what happened. And since one of the points of CompuCell is to be able to do things in real time in an interactive way, I like, for simple things like this that don't take too long to run, I like being able to run the parameter scan within a single simulation so I can see the results in real time, just the way you did the simulation where you were updating your estimates of the persistence length in real time. You kept updating them. Here, I'm updating my estimates in real time. Now, if I was going to be very serious and do thousands of replicates, well, I wouldn't want to do it in one simulation. I'd write a script to do it outside of that. But the fact that you can do these evaluations inside of a single simulation, I think, can be useful. So that really was what I wanted to get across here. And I think it's interesting to, here I've zoomed in. I've said, okay, the range for this particular situation, the range of parameters I'm interested in is, I can't read it here, 1/10 to the fourth. And again, you can see that for small, if the lambda is too small, the cell gets stuck. If lambda is too big, the speed saturates. But then there's a pretty good range of lambda for which you get linear force-velocity relation. So that's the region that you want to live in for your simulations. Again, in PhysiCell, you probably wouldn't have this low-speed regime here because there'd be no lattice pinning. You, instead of getting this kind of saturation for high forces, probably the thing would actually crash. PhysiCell would crash because there'd be a numerical divergence because your time step was screwy. Maybe it does an auto check on that, in which case you wouldn't get that. You'd be able to extend it. But in CompuCell, there's an absolute speed limit. And here that speed limit is about 0.24 lattice sites per Monte Carlo step. So the next thing that I wanted to talk about was the adaptation of lambda chemo. And I don't think we got to this in class last week, did we? We talked about it, but we didn't do it.
This is also a requirement.
Right. Did you do this homework assignment?
Yeah, I just changed this, I changed the XML.
Right. Okay. So were you able to see this where if you had an exponential chemical field, the cell moves very, very slowly at first and then speeds up and runs into the edge. Did you get that?
Yeah.
If you want to screen share, we can go back to your screen share.
Yes, I changed. I was just
Yeah.
Yeah, so I just changed the initial concentration expression.
Right. Well, actually, all you have to, well, what you need to do is introduce the decay. Well, you could, if your diffusion constant is 0, yes, then you could just introduce an exponential concentration. That will work. Yes, that's fine. And so what happens when you run that? Oh, you're using the multi-lane one.
Yeah, multi-lane.
Okay.
So it's a gradient distribution, it's like that.
Yeah, that length is maybe a little too short. It's gonna take you a very long time for the cells to see anything.
Indeed, like the cells, I have like encountered a lot of cases that the cell barely moves.
Right,
This drug, but I'm not sure I'll go with this one. You can see
Right.
that these are all instantaneous.
right. Basically, the cells aren't moving. It's just the random fluctuation. Oh, they're moving now. Okay.
Probably because I just tuned the lambda chemotaxis.
That's fine, yeah.
And because it's I think like that's because I didn't set a very appropriate parameter here.
Right.
Because the like with different lambda, they're just moving with the same speed, like near the same speed.
Well, so in that case, the lambda is so big that they're saturated, the velocity is saturated.
Oh, so that's, yeah, that makes sense.
And you see that here. If you look at this curve here, you see when it gets steep, it doesn't get infinitely steep. There's a maximum slope, which is the saturation speed of the system.
I see.
So,
but for
you have a plot just of the position of the cells versus time.
this one, there's the position versus
That's velocity versus time, position.
position.
And actually, that's not velocity versus position. It's labeled that way, but it's actually velocity versus time. Yeah.
No, this is position.
It
You
is?
see like the biggest coordinates here is a 400 and the length is.
So how are you estimating velocity?
I think these are all instantaneous velocity.
Okay, so one thing you have to watch out for again in CompuCell is that the probability of going forward and then backward a tiny bit is very high. So instantaneous velocity over one Monte Carlo step is almost never meaningful.
Okay.
Now, if you do 5 Monte Carlo steps or 10 Monte Carlo steps, that usually gives you something more meaningful. But over one Monte Carlo step, the likelihood is that the instantaneous velocity is near zero because of this funny anti-correlation.
So like the mean velocity is
Zero.
Yeah, it's based on the calculation of the instantaneous. So
Yeah.
one step for
Right. So again, my advice would be to start by just plotting the position of the cell versus time. And you should see more or less what you saw. My field is reversed from yours. I have the high concentration on the left and the low concentration on the right. But you should see the same thing. When you start at low concentration, the speed is very low, and then the cell accelerates and reaches its maximal speed. And if lambda chemo is very strong, actually the cell will break apart when the field is too big.
Yeah.
And so you can see that. So that one is pretty. That one is basically okay. So now let me come. I have to borrow the screen share back. So now what is actually quite useful, and it's something that we really should have as the default, is that there's an option called log scaled coefficient. And when you set log scale coefficient, then the simulation will automatically scale the lambda in response to the mean of the chemical field. the simplest thing though is to do something where, okay, so the first thing is what you've done, which is you create your exponential gradient. I would have used a slightly wider chemical field than you did, but that's okay. And then you have the cell move in that gradient. And you got something that looked like this. And so the cell moves almost doesn't move when the cell is in the low chemical field. Or to get it to move, you have to have lambda chemo to be very big. And in that case, it gets saturated when you're in the high field region. Alternatively, if you start out with lambda chemo small, the cell doesn't move at all in low fields, but moves moves okay in high fields. And so the next step here is to say that really you should be looking not at the gradient directly, but at the gradient divided by the concentration. And there are a couple of saturation options in the chemotaxis, which are not the ones you want. The one you want really is you want grad C divided by C. And you can do this by hand by making the initial lambda chemo to be some very big number. And then you measure the concentration of the chemical field at the center of mass of the cell. And then you divide lambda chemo by that concentration, divided by, if you don't have the 1 here, then you have a problem, because if the concentration goes to 0, this is divergent. So you have to have a number here to saturate it. And if you do that, then what you should see is that the speed of the cell is constant, even though the gradient is exponential. Were you able to get that linear speed?
Oh, I plot the position time. So I would like to try this
Okay.
rescale lambda.
Okay, yeah. So do you want me to give you a few minutes to try that?
Yeah, I can just try to open that project.
Okay, if you've got, oh, you've got it, you've already got it. Okay,
Yeah,
that's fine.
it's also like a
Well, again, I realized that these were homework problems, but I also thought it wasn't a bad thing to go over them with you. So if you had questions, if you said, "Oh, I have it all," that's fine. And if you had a question, I'd be able to answer it. You're not screen sharing yet.
Yeah, we're still like open.
Okay, that's fine.
Yeah, I think the used to be still, I'm not sure which one. So, try to run. So, oh, because I didn't draw the position plot, so you see this one. Oh, let me check.
So where is the position versus time plot?
Oh, I didn't draw the plot.
Okay.
So, but I can check whether this is an exponential. Yeah, this is as you said, this is a exponentially superior gradient.
Yep.
But the position,
I would add a position versus time plot.
okay, so we'll have that. But if I didn't scale the lambda parameters,
Oh, does each one of these have a different lambda?
yeah, each one.
Okay, so you're using Pedro's one.
So like before I rescale the lambda, that is the simulation that I showed you just now. Like all of the like all of them cells move.
Okay, but it's still interesting to have the position versus time plot.
Yeah, we can see that.
Because you'll get, each one of the cells will give you a different position versus time curve.
So like there is only one cell there.
Right, but it doesn't matter. It'll be fine. You'll see. You'll just add, so go to show your code and we'll do it
Okay.
together. Pedro, I think, wrote this code. It's a little fancy. And sometimes making it too fancy makes it a little, I like having the little racetrack, but it also makes it a little harder to see what's going on. So we'll add a plot. And this will be the position, X position versus time. And so the y-axis will be X position.
Yeah.
Y-axis title in line 113. I just call it X position. Okay. And you're going to have to make plot window and give it plot window a new number because it's got to be unique plot window.
Yeah.
I think you may already have 1 and 2 there, don't you?
No, I think names.
Okay, as long as the names are unique, they're okay, fine. Yeah. And just XCOM is what you want.
Yeah.
Okay, now let's go back to where you defined the plot for a second.
Oh,
It's almost never a good idea to use lines instead of dots in a plot.
oh,
And really, we'd like to color cycle it, but we're not going to do that for now. It would be nice if in the add data point, we could change the color. Okay, so let's see it run. Oops,
that's not
what happened?
two. Is it? Oh, because I didn't have it. Oh, here, yeah. But probably because I have multiple cells too.
Yeah, but it's okay. We want to have all the cells. There we are. Okay. What's the one at 250? I don't understand why there's a cell at 250.
That probably would like. So,
Yeah, it's a little hard. I mean, but you see they're different trajectories. One cell's moving faster, the next cell's moving a little slower, and so on.
yeah. So, it's like,
I'm not sure why there's a cell at 250.
I'm not sure. I think it probably goes.
Is there a wall or something like that?
I excluded all the wall type. So did I? I didn't. But wall cells shouldn't move.
Right, but they're still in the list. So you probably have to do for cell and self.cell list by type. So in line 46,
Yeah.
you need to do that by type.
Oh.
Yeah, the type name has to be in all caps, self dot type name, all caps.
It's a new out.
Okay.
Just combo one, so.
You probably didn't change the loop. Where did you put the by type loop?
Oh, okay. Probably because I.
Did you put it in the start function and not elsewhere?
Put it here instead.
I don't know where we are. That's in the start function.
It's
You
actually
don't care about the start function so much. You want to make sure it's in the step function. You only iterate over the cells that are the right kind.
Okay.
So you can copy line 46, and wherever you have for cell and self dot cell list, copy that and put it in. That's okay. Yeah, there you go.
We got this one. Right. Trying to assign different cell types, different colors.
That's okay. But yeah, that's where your problem was. Yeah. That looks okay. I think that'll be all right now.
It was like 1.3.
What happened? It didn't run. Okay. Now it's running.
Yeah, we'll just.
Oh, because you gave each cell a different cell type, right?
No, like each cell, like the cells, moving cells belong to the same type cell. And wall is another type.
Okay.
But just have two types.
So I don't know why it's not plotting your loop over cells isn't running for some reason. Where you're doing the plot of
I think it should not, because you just narrow the looping.
yeah, but it's not plotting what you're expecting. So let's see. Just where did you do the loop? For cell and self dot cell list by type. Okay. Yeah, so for some reason for cell and self dot cell list by type in line 133 is not working. Well, why is that not working? Oh, I know why. Look at line 146. Yeah. Oh no, that's the plot. That's the center position versus velocity. Where do you plot the position of the cell?
Oh, I plot a position on this.
Okay, so let's look at that loop. So why is line 189 not getting? Why is line 189 not getting called?
I think it's getting called, but it's just putting 1 point.
Right, but that shouldn't. It should have 1 point for each cell. And every 200 Monte Carlo steps, it should be adding a point. So that means that somehow cell that, can you open the XML for a second? Just. Yep, cell is right. Okay, so I'm confused. Let's go back. Let's go back to the simulation. Let's look at the code. Let's look at the run, the output of the simulation. So why is it not plotting the position versus time? Just click on that window.
Right click.
Anywhere, just no regular click, just click. So it's not a question of failing to update.
And I think it's also, we were just like drawing a plot at 11.
Well, that's probably the initial position of the cells.
Oh, probably.
So that's not necessarily wrong. Is the y-axis auto-scaled? Right-click on it. Let's just check the scaling of the y-axis. But also the Monte Carlo steps isn't being updated, right? It's never showing you Monte Carlo step 200. Look at the x-axis of the. Click on auto scale. There you go. You had somehow the settings and they were not right for the scale for the axes. I don't know why it was set to not auto scale. Okay, fine. So now you can see the trajectories of each cell quite clearly, right?
Oh yeah, because they're returning.
When it gets to the end, it flips the sign of the lambda, like my code. But you could see that, look at the lowest couple, as you increase lambda, the speed goes up. But then for big lambda, they're all on top of each other.
So big one then refers to these.
Yes. Yeah.
Yeah, but like you could check their velocity by the slope.
Yes.
So like even like their slopes are pretty close to each other. So
yeah. But the problem here is that the only one that's really interesting is that one at the bottom, the slow one. Yeah. Or maybe the one immediately above it where you see it's slow and then it speeds up.
Yeah.
Okay. So now the next step in this exercise, again, left and right are reversed in my plots from yours. So, but the curve that you're seeing in my plot is like the third one from the bottom in your plot, where it starts slow and then it speeds up. Now that's what you're seeing. So if you move your cursor up to the third line above the one you're in, then that one, yeah, that curve there is like the curve I have on my screen.
In that part?
Yeah.
Oh,
Remember, left and right are reversed. So I mean, sorry, in this case, top and bottom are reversed. So it's slow and then it speeds up.
Yeah, but so you think like it's weird?
No, this is normal, but this is the response to exponential. So now what you have to do, is you have to go in and you have to adjust the exercise. The exercise is measure the concentration of the chemical field at the center of mass. And then multiply lambda chemo by 1/1 plus concentration at the center of mass.
Wait, I think this one has already
You've done that already?
scale, yeah, like the C scale here is assigned as, oh, it's a little bit different, but
Okay, so how did you do it?
so C scale is 0.5.
Yes.
Yeah, I just calculate a base number.
Okay,
Because
so you
it
did
is
this
a-
already. Okay, fine. So this is already rescaled?
Yeah.
Huh.
So with the exponential gradients, they could just
Okay.
perform as linearly.
Okay, then I would have expected them to be more linear than they are.
Or I could just C scale.
Well, let's try one. So, I mean, maybe this exercise then was a mistake because the purpose of this exercise was to do this by hand first. And then to say, well, CompuCell actually lets you do it automatically. When you do chemotaxis, you set log scale coefficient equal to 1.
So
Then you don't have to automatically update the lambda by hand. The CompuCell will do that for you. So why don't you try doing that? So you need to set in the XML, you could set log scale coefficient equal to 1.
and then I had to remove all the codes in the Python because it was.
So now that I don't remember. Pedro, if you're there.
Yeah.
When you do in chemotaxis, are you allowed, when you have it set in the XML, can you overwrite in Python or not?
Yes, you can.
Yeah, so in this case, you're allowed to do it, so it should work. If it fails, I want to know. So go to the in the chemotaxis plugin, you would have chemotaxis by type equals cell, lambda equals 100, log scale coefficient equals 1. And then you're still allowed to change the value of lambda in the XML, I mean in the Python, I believe.
Yeah, but like after Python rewrites the value, shouldn't the program just follow the value created in Python?
Right, but it's not gonna change the log scale coefficient.
Oh, yeah. Mhm.
Now, what I don't remember is how you reference log scale coefficient in the Python. Do you remember the name of log scale coefficient in Python? We can look it up online. We do in principle have reference manuals. Whether they're right is another question. We could check. Did it work? No?
Yeah, it's I think I'm sharing the screen and
But the moment the moment I'm sharing screen, let's see, let's go back to yours. Okay.
okay, so let's just wait a couple seconds.
Yeah, those look pretty linear now. Yeah. Maybe the bottom one is a little bit stuck, but they're pretty linear.
Yeah, like I think like the top one is totally influenced by the output function because I didn't draw a line at the top.
Oh, yeah, no, it can get stuck on the boundary.
Yeah.
Yes. Yeah.
Like drag.
Yeah.
Before the rest of that,
Yeah.
like the velocity, it would not be affected by the boundary.
I'm still a little surprised the velocity is saturating like that, but Well, now it looks okay. So now let's see what happens. So
I think for this.
there we go. Yeah, this looks fine. They're all basically straight lines. It's not perfect, but
Yeah, basically.
the first one is stuck. Until it gets started, it's stuck. So the first few points are delayed, but it's pretty linear. And then it's now reversing direction. The top one is reversing direction.
No, I think they just kind of get stuck here. I don't know. Probably like my reversing code because I adjusted a couple times, so sometimes it
Right.
works, sometimes it doesn't.
But the main point here is just that when you use the log scaling, you get essentially a linear velocity force, you get a linear speed even for exponential chemical field. That's really the point. So you get a linear speed for that. And you can play with that a little bit more. And I would look up in the manual how you set the log scaled chemotaxis parameter in Python, because I don't remember as you point out, you should be able to do it in Python, not just in XML, and I don't remember the command for it. It's in the manual, but I don't remember.
Oh, I mean, like, my question is not targeted as like towards the log scale that part.
Right.
The question is like in XML,
Yes.
it allows you to use the plugin to adjust the lambda, right?
Right.
To scale the lambda. And in your Python code, you're again like doing adjustments to the lambda.
Right.
So like,
Well, I wouldn't know. So if you use the log scaled chemotaxis in the XML, don't divide by the center of mass concentration. Turn that off. It will do it automatically for you.
oh, but I just keep them.
Oh, so you're doing it twice, basically.
Yeah.
Okay, so yeah, so turn off all the special code in the Python.
So that wouldn't generate an error, but technically they would generate error. They just like calculate it twice.
Right.
So it would just have like influence on your result.
Right.
Okay, I see. Yeah, that makes sense.
So maybe that homework exercise was too smart for its own good. Basically, what I wanted people to do was, first you have a single cell. The problem is we used Pedro's code. We should never have used Pedro's code because it's too complicated. Pedro is a little bit like ChatGPT. It writes very beautiful code, but it writes very, very complicated code. And so it looks gorgeous and the results are beautiful, but learning it with it maybe is a little hard because it's got too many things going on. So the concept of this exercise was you have one cell, you put it in an exponential field, and you see that at the low end of the exponential field, it doesn't move. At the high end, it moves too fast.
Yeah.
And then by hand, we say, okay, now we're going to adjust lambda by hand based on the center of mass concentration. And then we see that works pretty well. And then we say, well, actually, that's built-in function in CompuCell. Instead of adjusting lambda by hand at every time step, we just tell CompuCell to adjust lambda at every time step. And so that was the idea of the exercise. And I guess I made it too complicated. In other words, if I just said, here, create one cell, turn on turn on exponential correction, and it works, then we would have, instead of trying to walk people through, I want people basically to see the derivation of why you use the correction factor. So I'm sorry, I outsmarted myself on that exercise. And then because Pedro has this beautiful simulation where you have the channels with lots of different examples running simultaneously, then it's a little harder to see. You have to change things in many places to get everything to work. So again, Pedro's racetrack is really nice, but it makes it a little harder to see the simple thing that I was trying to see. So let's do my favorite example, which is angiogenesis. And for angiogenesis, I think I gave you a homework problem on that, right? No?
No.
I gave you the bacterium macrophage homework problem,
Yeah.
right? So that's the next one. So the angiogenesis, of course, if we look at our body, I mean, you can see blood vessels here in your hand, for example. And the question is, how do those develop in an embryo? And also, for example, in cancer, when you have neoangiogenesis, when you have new blood vessels, or if you have an injury where you kill the blood vessels and the blood vessels have to grow back, what is the basic process of angiogenesis? Now, it winds up that there are two different kinds of formation of blood vessels in the body. They both involve the same kind of cell, which is called a vascular endothelial cell, EC for short, capital E, capital C for endothelial cell. And you have what is called sprouting angiogenesis, which is where you have an existing blood vessel and you get a branch on that blood vessel that then forms a new blood vessel. And you have what's called primary vasculogenesis. Vasculo and angio are actually synonyms. They mean the same thing. They both mean blood vessel. And if I remember right, I think vasculo is the Latin and angio is the Greek, but in any case, it's a little bit like Japanese, where every word has the Tang Dynasty pronunciation of the Chinese and the Japanese pronunciation of the Chinese.
Oh, yeah.
So every word has two pronunciations. The onyomi and the kunyomi.
Yeah, indeed. Yeah, indeed.
Right. So in English, a lot of times you'll have two words with the same meaning, one derived from German and one derived from Latin, or one derived from Greek and one derived from Latin. And so you'll run into that. But in any case, in vasculogenesis, instead of having an existing blood vessel that sprouts, the individual endothelial cells are initially randomly distributed, and they gradually cluster to make blood vessels. So in one case, you basically have a clump of endothelial cells that sends out branches. In the other case, they start out separated and they come together. And then there are things like the formation of tubes and vascular remodeling, and there are other cell types that are important too. But early on, really, it's the endothelial cells. And those are derived from mesodermal precursor cells, and there's a particular set of gene expression that you could look at in the precursor cells. The blood cells also come from the same precursors. So they're what in the peripheral tissue, like the limbs, they're what are called blood islands. And those produce both the blood vessels and the blood. Now, the major blood vessels, like the capillaries, form in a different way. I mean, so capillaries, the aorta form in a different way. The capillaries form. Okay. And so something that we wanted to know about from the beginning was whether it's the same cell type. We know that it's the same cell type, whether the same mechanism was giving rise to both kind of patterns. And here is sprouting angiogenesis. This was a movie that was made by Sherry Clendenin, who was when I had a wet lab, she was the lab manager, very good microscopist. And this is actually live imaging in a fish. And you see the blood vessels. These are the intersegmental vessels. You see that they start on the bottom and they grow up, and then they connect to each other. So that's actually watching what happens. You can also see initially the endothelial cells are solid, and then they gradually turn into tubes. You see? They're hollow at the end. They start out as struts, and then they become hollow. And we're not going to be able to simulate the formation of the tubes. That's not something we can do here. You can also see, if you look at this carefully, the cells are the dark spots are the nuclei. That's the nucleus of the cell. And so these cells are actually very elongated and flat. If you fry an egg, where you have the egg, the white of the egg is flat, and then the yolk sticks up in the middle, that's the black is the nucleus sticks up, and the rest of the cell is very flat. And CompuCell is not very good at representing that kind of cell shape, so we are not going to do that. But one could think about how to do that. We're going to focus more. Now, here is vasculogenesis. Initially, the cells are, that's showing that they make tubes also. Let's go back to the beginning of this movie. So here we have endothelial cells that have been put in a culture dish, and they're randomly initially, the initial positions are random. And they're not quite random because it's not time zero. You could see they're stretching out to connect to each other. And as time goes on, they cluster and they form little struts. And then the struts gradually rearrange. And this is actually happening in your body too. The large blood vessels in your body don't move around, but the very small blood vessels, the capillaries, actually rearrange during your life. They continually rearrange. Be in your body, there are additional cell types called parasites that will be attracted by these cells and surround them and stabilize the blood vessels, so there's less movement. And for large blood vessels, there are additional smooth muscle cells that surround that stabilize. But for capillaries, the initial capillary formation, you get a lot of reorganization. And even in the adult, there's continual rearrangement of capillaries in the body. And so these are the things that we want to be able to simulate, that formation of not the making of the tubes, which is the later part of this movie, but the early organization. And so the key question is, if we look in vitro, in 3 to 6 hours, these endothelial cells migrate, and they actually stay round until they start connecting to each other. And then they form this continual network. And then, in this case, it's a 2D experiment. You have a substrate, and the cells stay on top of the substrate. In a tissue, they form a 3D network instead of a 2D. And we'd like to know, how does the cell density, the initial cell density change? What happens? the cells clearly stick to each other. How does that change things? The hypothesis here is that there's a chemical interaction, there's a chemical attraction between the cells. Because if you take two endothelial cells that are separated from each other, they come together. Now, they could interact in a variety of ways. One way is they could just secrete a chemical into the environment, and the other cell sees it through chemotaxis, which is our hypothesis. But they could also be sending out very fine filopodia that we don't see, and actually actively pulling at each other. So filopodia are, sorry?
Flagellum.
They're like flagella, yes. They're the eukaryotic cells don't have different, yes. So they're like flagella, yes. And actually, what is it? Is it type 4 pili that do that? Bacteria will do that too. I think it's type 4, where the bacteria put out a fiber, and the fiber anchors, and then they shorten the fiber and pull on it.
Yeah.
I think it's a type 4 pilus. I don't remember. There's type 1, type 2, type 3, type 4, type 5. I think it's type 4. But filopodia basically work like this. If I had a rope with a hook on the end, and I throw the rope and I hook onto you, and now I pull to pull myself towards you. That's how filopodia work. I think it's a type 4 pilus. You could check. So there's an analogy in bacteria as well. And we couldn't really tell the difference. We can't, in the imaging that we're doing, we couldn't see the filopodia are so fine, are so narrow, we can't see them in this microscope. And they could also be interacting by changing the extracellular matrix. They could be creating stress in the extracellular matrix that sends a signal. So for us, the idea of chemoattractant is that there is some attraction that decreases as you go far from the cell. And the mechanism we're hypothesizing is chemical, but there are other people who've hypothesized filopodial pulling or extracellular matrix attention. And then one thing we'd like to be able to do also is, if we have a picture of blood vessels, could we infer what the parameters in the simulation are? And the question is, why would we want to do that? And one reason is that when we look at blood vessels in the eye, for example, there are diseases that disorganize the blood vessels. And we'd like to be able to do diagnosis. And one way to do the diagnosis is to say, if this were a simulation, what are the parameters? Are they normal or not? Also in cancer, you get the same sort of thing. And actually, we're working with a student at University of Virginia now using AI to try to do this inference. Okay, and so there are these different models that have been published going back to George Oster and Murray in the 80s. The mechanical pulling models and others. And we're based on a model that was originally published 20 years ago by Gamba and Serini on chemotaxis. And there's a very simple observation going back in their paper of Gamba and Serini, where they said, they couldn't measure the chemical concentration directly, but they said, if the cells were secreting a chemical, and the cells were moving in response to the chemical, how would the cells move? And they were able to show that the experimental movement of the cells behaved as if the cells were secreting a chemical. So even though they couldn't see the chemical, They did a simulation that said, here are the positions of the cells. Let's imagine they all secrete the chemical. Let's calculate what the chemical field would have been if they secreted it. And now say, okay, if the cells chemotax up the gradient of the chemical, what would their speed be? And then they showed that that agreed with the experiment. So they were able to infer that there was an attraction produced by the cells. Now, if the cells were pulling on each other with some other mechanism, the force would still be the same. So it doesn't prove that it's a chemical field. It does prove that it's an attractive field that surrounds every cell and decreases as you go farther away from the cell. And then they built a reaction diffusion equation model of it. We don't have to go into a lot of detail about it, but they essentially assumed linear chemotaxis. And that works up to a point, but not completely. And so we started with that idea that the cells secrete a chemical. We called it VEGF-A, vascular endothelial growth factor A. And that is because we know that the cells secrete that signaling molecule. And there was an additional experiment that was done by collaborators of ours, Erica Perrin and Charlie Little, which showed that if you interfered with the cadherins, the cell adhesion molecules, then instead of getting the vascular patterning, you got just clumps of cells. And the key thing about that is that the VE cadherin does what's called contact inhibition of chemotaxis. So where you have VE cadherin, the surfaces of the cells that are contacting the medium respond to the chemical, but the surfaces of the cells that are contacting each other don't respond to the chemical. And that's actually why we have specifically the flag chemotax towards medium as an option to implement this model. But it's a general property of the and that was something that our collaborators showed experimentally. So they're not very pretty here maybe now, but they did experiments where they turned off VE cadherin and showed that you get clusters of cells. And so we have just two kinds of things in this model. We have endothelial cells and the growth and the VEGF field. And we're imagining them crawling on a substrate, but it'll be a 2D model to begin with. The cells move randomly. They have a volume. In some versions of the simulation, the cells elongate. They stick to each other, so they have a contact energy. The VEGF field diffuses and decays, as fields do. And then the endothelial cells secrete VEGF-A, and they also chemotax towards VEGF-A. And the endothelial cells stick to each other with contact inhibition of chemotaxis. And that's it. And this is the mathematics of that model. We don't have to think about that for the moment. We used a saturated chemotaxis here. So we used a saturated. And this is a strange saturation. It's not the correct one, I should say. But this is the old one that we used in those papers. And this is the simulation. And so in this simulation, if we start with randomly positioned cells, and we have all the cells everywhere responding to the chemical, they make blobs. And if we have the cells have contact inhibition, they make the vascular pattern. And you can ask, for example, what is the diffusion length you need to get the pattern? And the answer is the diffusion length has to be very short. The width of these struts here is proportional to the diffusion length of the chemical. So if you make the diffusion length too big, you get blobs also. And so one of my old students, Abbas Sharinafard, in his PhD, this unfortunately was never published, was actually able to show that the same mechanism works if you start with a big cluster of cells instead of individual cells. If you have a big cluster of cells in dips in the cluster, there's a strong force inward, and in peaks in this cluster, there's a strong force outward. And so there's an instability where an initial cluster of cells will generate sprouts. So he was able to show that. And this nice thing about this mechanism also, if this runs, doesn't want to run, huh? This movie doesn't want to run. There's a codec problem with it, I guess. Yeah, we can run this we can do this in class. It says codec not support. The same mechanism works in 2D and 3D with no changes, which is sort of unusual. Normally you have to make some changes when you go from 2D to 3D. Sorry?
Why would you like add changes if you like transfer from 2D to 3D?
Well, that's a reasonable question. I'm not making it as a scientific hypothesis. I'm making it as an observation. That usually when you write the simulation in 2D and you say, now I want to make it 3D, I have to change a lot of things.
So maybe on the scale?
Mainly of scale, yes. The numerical values. For example, the volume of the cells has to be bigger in 3D. If the cell was 5 microns by 5 microns, and you now make it in 3D, it has to be 5 by 5 by 5. And the contact energies change, the fluctuation amplitudes change. And some things really are different because in 2D, if you have a barrier, a cell can only get through the barrier by breaking the barrier and then having it reform. Whereas in 3D, you can go around it. And so actually movement in 3D is easier than in 2D. In a crowded environment, you have much more movement is much easier in 3D than in 2D. And so things like if you want to have immune cells tracking targets or your bacteria moving around things, the way they move in 3D and 2D is quite different. It's not just quantitative, there's qualitative differences. So the angiogenesis simulation, and there is a demo of this, but we can do this by hand. Let's build a 256 squared lattice and create 7 by 7 cells in a square grid separated by a gap of 4. We'll call the cells endothelial cells. We'll have one chemical field, VEGF. The cells will have contact energy, volume. We all have the same volume. We all have chemotaxis.
Okay, just
And then this EC is chemotax only towards medium. And then we have the, and let me fix this because there's a typo in this slide. And I should say that this simulation was done originally by Roland Merks, who's now the head of computational biology at Leiden University in the Netherlands. There, fix the type.
So so what is your setting all the boundary conditions of the
Periodic. both for the cells and for the chemical field.
I'm sorry, what is the NSAT of sixth flow?
I'm sorry?
Like stack chemotaxis of VC cells. VGF wheels towards medium set.
Oh, it's probably just
Also,
what happened there.
sorry.
And in this case, I did everything in the XML. That's because this is a very, very old simulation. So when we did this, we didn't have Python. We only had the X.
But now like you have to add like secretion part in.
No, you can do it in the Python. You can do it in the XML.
So
Again, since every cell is going to be identical in this simulation, it's reasonable to do everything in the XML.
Why is it like, because it's identical? So
every cell behaves the same way.
Okay.
All the cells have the same volume, all the cells have the same chemical response, all the cells have the same secretion. And so we don't have to change one cell at a time. Although for more sophisticated simulations, we might very well want the end. In fact, the endothelial cells do reproduce, they do grow and reproduce, and they do change their behavior. So in a more sophisticated simulation, we might very well want to use Python. But for now, we can do everything in the XML. Right, right.
So inside EC, there is no diffusion, where the diffusion is just the same as the global.
Yeah, we're not going to change.
Okay.
Now there's some. Now in this particular one, I said global diffusion is 1. Global decay is 0.3, and that there's no decay inside the endothelial cells. There are various versions of this simulation that have been done over the years that make different choices about these things. And all of them will give the same general kind of patterning, but the details of the patterning will depend on, is there diffusion inside the cell, or is it different inside and outside the cell? Is there decay inside and outside the cell? All of those give slightly different results. But let's just try this one. Maybe this one won't work because I forgot. It's so old that I've forgotten, but I think it should work. So what does it do? Let's see. Let me stop the share and I can see.
So like all of the other parameters are as default. I didn't change like the content.
Right, that's fine. Can we see the?
Okay, I'll screen share. Okay, so I'll just
Yeah, that doesn't look too bad. So the one thing, can you start it over?
Oh, it's pretty clear.
Why don't you hit stop and then hit just step and then we can start.
Okay, so.
Okay, so you're starting with all the cells clustered in the center. And they're not separated from each other, right? I mean, that's legitimate. That would be the sprouting angiogenesis. And it actually does produce a vascular pattern. You see the vascular pattern. But let's try having the go to, why don't you make the cells everywhere? So go box mid zero, and box max 256. Okay, then 256, and it should be 6. Doesn't matter. If there's one off, it doesn't. Try that. Let's see what we got. That may be too many cells. Let's see what happens.
Maybe the gap is.
Okay, let's run it now. Yeah, now they're making, okay, that looks more like this. So you see they reach out and make struts, and then they gradually, the struts will come together. You need to hit run again when you add a image, you have to hit run again. So they definitely are building vascular branches. And when you start with the cluster in the middle, it actually sprouts out pretty nicely too. Now, so there are games you could play here. One game you could play quickly without having to start the simulation over again is if you go to the properties in Twit, I mean not Twit, in Player, go to that model editor, and where you have go to the diffusion solver. Where's the diffusion solver? Yeah. It's there somewhere. Okay, diffusion solver FE, there we go. And now open up diffusion field.
Yeah.
And now you have to go to diffusion data, it's sort of hiding. And now make the global diffusion constant bigger, like make it 10. And you probably have to do the same thing for the other one, the diffusion constant inside the cells. Yeah. Make that 10. Okay. And now hit run. Now you see the field has gotten much more spread out. And let's see what happens to the pattern of the cells as it runs. You see they get, well, the struts get wider. You see they're fattening up. Yeah. And so the diffusion length controls the width of the struts. And there are regimes in which this thing will collapse into a big blob. This may be one of them. I picked the numbers at random. I didn't. Okay. You can also play with the adhesion between the cells, which makes a difference.
Just adding the parameter of the contact energy.
Right, so changing the contact energy. If the cells stick to each other too much, you get blobs. If they don't stick to each other enough, you never get clustering at all. So there's a balance there. The other one that's interesting to do is let's get rid of the chemotax towards medium and let it chemotax towards any. So if we go back to the XML where we say chemotaxis, where's the chemotaxis definition?
and like time.
Yeah. No, actually, you don't have chemotaxis towards medium, huh? And it's still working. That's interesting. I'm actually quite interested that that worked. Shouldn't have worked.
Do you want to like change it to mediums? See like what change?
So you have actually chemotaxis on all of the surfaces. So you have no contact inhibition of chemotaxis. And it's still working. That's interesting. I wouldn't have expected that.
So, wait. I'm still like processing this.
So if you look at line 6 in the instructions here, you have chemotaxis of ECs in the VEGF field, but you don't have only towards medium. You don't have that. If you look at line 58, you have chemotaxis on all surfaces. And so it's interesting to me that that works. I would have expected it would fail.
So what you expect is that
Blobs.
here's like all of the cells like it's like cell only says the chemotaxis train on the
Free
surface.
surfaces.
Free surface.
Yeah.
Oh,
And in your simulation, they sense it everywhere.
yeah.
And so I would have expected that the simulation would fail. And well, it's a little blobby, but it's still making struts. So why don't we try changing it to be chemotaxis towards medium?
I need to like figure out how to.
You could just replace just try replacing the chemotaxis plugin.
Oh,
So in the CC3DML,
yes.
chemotaxis. Oh, what happened? Did you? Okay. Okay, there we go.
So here is medium.
Yeah.
You just want to keep that one and out all of the other ones.
And then you need cell type. So you still need, in type, you need the cell type. You need EC. And what was the value that we had of the chemical, of the chemotaxis parameter was 500. And then you better get rid of lines. Comment those out. I was going to say, don't erase them, comment them out. Well, you can always generate them again. Okay, try that. See how what happens with this. It may not be any different. Maybe it'll be exactly the same. Let's try again. Oh, in line 57, you didn't put in the name of the field.
Oh yeah.
VEGF. Texture is a little different. Not a lot different, but it's a little different. The pattern is more connected. In the other one, there were more long lines. In particular, what you're seeing here is sprouting. You see how, I wish I could, I can't point on your screen because I don't have, can you enable a screen, can you enable annotation by others? In your Zoom? Where the three dots at the bottom of the screen for your Zoom controls, you should have enable annotation by others.
Oh, okay, I see.
There we are. That's fine.
Okay.
So now let's see, where's the highlighter? There we go. So you see here where I'm pointing,
Mhm.
you see that line that's coming up and it's growing and it's going to bump into the far side of that
Mhm.
like that.
Yeah.
Or up here, there's one
Mhm.
there. That's a sprout. Or down here, there's a sprout.
Mhm.
Those were not happening when you didn't have that restriction to chemotaxis towards medium. So you were still getting the formation of lines, but you were not getting sprouting.
That's why like the lumen
Right.
between this faster is
Right.
super wider. Like,
That's right. And if you look in the experiment, you get sprouting a lot. This is closer to what really happens. So initially it doesn't look very different, but as it keeps going, it gets quite different. And so that's what I wanted to emphasize. So it's quite a different result. They both make clusters, but the result is quite different. Now let's go back to the chemical field and make the same change. Let's make the diffusion length longer. No, in player. So go to the diffusion solver and open that, and then go to diffusion field. Okay, global diffusion constant, make that 10 instead of 1.
Oh.
Now I think we'll see, but I think you'll see a big change. Maybe not. Let's see what happens. It may take a while, but you should see the pattern collapse.
I think like some like the edges are beginning to
Merge together.
yeah.
It takes a while for the pattern to rearrange, but it does.
The smaller.
Yeah.
Like the smaller
Domains. Those are called lacunae. Lacunae. Yeah.
Are disappearing.
Yeah. And you'll notice the width of the struts are getting wider. If you look, it's instead of 1 cell across, it's now 3 or 4 cells across. So this is actually a pretty powerful simulation. If you also add the cells being elongated, because as you saw in the experiment, the cells stretch out, not immediately, but with time they stretch out. If you add the elongated cells, then you get even more complex behaviors. And again, there's some things in CompuCell that were written specifically for this simulation. So there is something called connectivity constraint, and that was written specifically to allow you to have very elongated cells in this simulation. You remember that when you put a length constraint on the cells, if you made that too big, the cell would split into 2 pieces. So the connectivity constraint forces the system not to let the cell split.
Oh,
Right.
the operation.
Right. And so that for the cells that with no length constraint, you don't need it. But if you want to make the cells be elongated, you need it. So this is the basic simulation, and let's come back to the slides for a second. And we tried with chemotaxis. We did it with chemotaxis everywhere, and then chemotaxis towards medium. Another thing you could do is to change the density of the cells, the initial density of the cells. If the initial density of the cell is too low, then the cells don't really cluster. They don't find each other. It takes a long time to find each other. So if you rerun it with a gap of 10 instead of 4, you'll see, try that. You'll just try it. So change the gap size in the initial condition to. Right. And you also tried one where you had the cells in the center and then they sprouted out into the periphery. So that's another one you could try. But first one, try making the separation between the cells bigger and see what happens.
Yeah. This is presenting the gaps with.
Right. Yeah, okay.
Yeah. I'm pretty sure
yeah. So that they find each other locally and eventually they will connect, but it takes a long time. Because the diffusion field is short, so they don't find each other over long distances. And so there is a dependence on the density. And now let's go back to the higher density. And so let's go, still editing the box, the blob, the uniform initializer, but let's make the gap 0. But now let's make a square of cells in the middle. So like make it 50, 50, 250 on the other side, something like that. Sorry, 200 on the other side. No, better make it 200. Okay, good. Okay, good. Try that. So this is now going to be sprouting angiogenesis.
Forgive me, but I think we had the room reserved.
No, we have it booked. We
Well-
have this room booked every Tuesday from 2 till 6.
Okay. 4004.
Yeah, something is messed up because we have it booked.
Mm.
Yeah, so I just think the simulation parameter.
Yeah,
Well, we'll just behave as the.
yeah. So that's the sprouting angiogenesis. Yeah. So you can see the simulation. Now, I don't know what we're going to do. If they've got this room, if there's a conflict over this room, I don't know what we're going to do. I booked it for the whole semester, so I don't know what. I mean, we could go to the classroom, but the problem is that I don't have the key for it at the moment. So let me see. I wonder what happened. Let me look.
Just administer chat.
Sorry?
Oh, you can just administer chat. It's okay.
Well, I mean, we're also almost at the, I mean,
Yeah.
we could end a little bit early today. I'm more worried about what will happen next week if this is an ongoing problem.
Honestly, like if this classroom, like if we have problem like preserving it, you can go to Miles Brown Hall, like the 3rd floor. There's an empty classroom, and actually, like around my workspace, like nearly no person would show up there.
Right, well, there are plenty of places we could do it. It was just, I picked this because it was next to the. I picked it because it's next to that, but I'm just. I don't know what happened to the room. Anyway, let's give it. They can also find another room, but it's more of a question of what happens going forward. I don't even remember what the name of the. What's the name of the reservation system? I'm looking online to see. Mhm. I don't like to interrupt the class to do it. I can't think of the name of the reservation system for the room. Search doesn't.
I think it's called Loving Room Reservations.
It's possible. Because I can't, I'm trying to find in my email the reservation confirmation, and I don't remember what the search term is for it. No, it has something funny like 47 or something else. I can't remember it doesn't matter. We'll let them deal with it for the moment. Let me look. Yeah, light school room reservations. Where is it?
Excuse me, but we actually do have the room reserved.
So there's some conflict because I booked this room from the beginning of the semester. And
Tuesday, 5:30 p.m.
yeah, it shouldn't be giving you that because we had it booked till 6.
How long is your?
It's for a grading session. We have like 68.
Well, I'm trying to find my email because as I say, I did this at the beginning of the semester
Okay,
and it was booked for the whole semester.
okay. It's somehow the system allowed us to do it. I let she had me do it, so I'm not sure I have to do it myself. But that's a Tuesday, 3rd, 5:30.
Yeah, I know there's a problem. They somehow it didn't.
But you're going to be done at 6, you said, more or
Yeah.
less? Okay, that's okay. We can.
I'm sorry about that, but I mean, as I say, we've been using this room, every Tuesday from 2 to 6 since the beginning of the semester. And I booked it the first week of the semester for this meeting.
So
And so I don't understand. I mean,
It's okay.
we should figure out what happened because obviously.
You might want to figure that as well, because if it's not reserved for you, then somebody else will try to do this later. So
Right, that's what I'm concerned about. I'm sorry for you. I mean,
It's okay.
the principal at this time, it shouldn't be that hard to find a room, but it's just,
Right.
it's just,
Yes, yeah, that's why.
okay.
But it's okay.
but yeah. We can always go back to the classroom, which we have. And the reason I booked this was because the classroom, we didn't know whether the classroom would be available earlier, although it seems to be. But I really am confused about that. I wonder if there are two reservation systems anyway. Let's not worry about that. Let's just get another 10 minutes of class and then we'll I don't want to lose the rest of the time we have.
So, yeah, like, do you want to go back to the?
Yeah, let's go back to the simulation.
So much different. So this is so far good.
Yeah, so that looks pretty. This was starting with the blob, right?
Yeah,
And you see after a certain amount of time, you can't tell what the initial condition was.
there's a shrink, and then like it just branches out from the,
Yeah.
especially from the
Yeah.
corner.
Yeah. So I wasn't actually going to show those simulations, to show those slides, but I will since we're going to run out of time. We're not going to get to do some of the other things that I wanted to do because of the time. But I mean, in principle, this class only is not 2.5 hours anyway. So you know, but we normally run longer because you're interested, but in fact,
Because I spend a lot of time talking.
that's fine. But I want to give you the time you want, and so I'm sorry about losing the. I don't know why this slideshow doesn't want to. What happened there? Why is it not?
It's kind of like stuck on the monitor. Oh, it's fine.
I don't know why they. All right. So you can do parameter sensitivity analysis here where this is an example where we've changed the cell-cell adhesion. So you change the contact energies and you see the different patterns you get. If you make the cells stick too much to each other, you get blobs. As you make the contact energy less, you get thinner struts. Here is the strength of the chemotaxis. If the chemotaxis is too weak, obviously you don't get any patterning. If the chemotaxis is strong, you get narrower struts. And then we didn't use the saturated chemotaxis, but if you use saturation with contact inhibition, which we have, and saturation, you can get different patterns as well. So whether you use the logarithmic saturation, the Michaelis saturation for the chemical response, you can get that. And then this is changing the diffusion length. And again, you get these different patterns. So there's a whole zoology of different patterns that you can get by changing the parameters in the system. There are quite a few. This is one simulation where we actually put the length constraint in. And in this case, you have to put in to get these very long cells, you have to put in the connectivity constraint. And so that's something that you can play with as well. So we're not going to have time to do this. Did you have time to try this exercise at home at all? This chemobacterium macrophage?
I'll go back and try it.
How did it work for you? Did you get it? Did you get anything for that?
I'm sorry, like, what do you mean, like, how?
Well, this was one of the homework problems.
Oh, okay.
And so I didn't know if you tried this homework problem yet.
Oh, I didn't try this.
Okay.
Um,
So what's happening here, this is a very famous old movie where they took blood and this is a macrophage. This is a bacteria. These are red blood cells that are not doing anything. And the bacterium is secreting a chemical which the macrophage recognizes, and the macrophage chases the bacterium. And the goal of the simulation is to write a simulation that replicates that behavior. Now, the one thing that you can't do in the basic simulation is you can't have the macrophage eat the bacterium, because engulfing the bacterium is something that you have to do as a special extra process. But the goal of the simulation then is to, I don't know why the movie has a sound in it,
to recover the process of chasing.
I guess. But again, you can build that simulation in steps. I guess it's a neutrophil. I said macrophage, it's a neutrophil. And we can then gradually build a more complex model. And so the steps here are in the slide deck. And something that's rather interesting is the initial simulation and the experiment only have one neutrophil and one bacterium. But if you have multiple bacteria, then you can have the cell chase one and then go chase a different one and chase a different one. And the other thing is that in reality, the bacteria is pushed away, but when the cell moves, the liquid gets displaced and that pushes the bacterium away from the cell that's chasing it by fluid dynamics. We don't have that. And so one way to implement that is to have the neutrophils secrete a repulsive chemical that pushes the bacterium away a little bit. And so that's the simulation there. All right, the next thing we were going to do is persistent movement. We're not going to get to do that today. So I think that's for today, that's all we're going to have time for. I will check on the Rube, try to figure out what happened to us today.